Hello, Vital Sign. Today we're going to examine two theorems involving clique polynomials. So if you haven't already, I suggest you watch my earlier video on clique polynomials. To recap, the clique polynomial of a graph G is one whose coefficients represent the number of cliques of each size in the graph. In my previous video, we saw the following expressions for clique polynomials, relating clique polynomials of graphs to clique polynomials of subgraphs. In this video, we're going to look at two theorems involving the roots of clique polynomials, making use of the expressions seen here. The first theorem, which makes use of the top expression, is this. Suppose we have some non-empty simple graph G. Then its clique polynomial has a real root, and the maximum real root of G's clique polynomial is greater than or equal to the maximum real root of any of its induced subgraphs' clique polynomials. To prove this, let P of n be the previous statement for a graph on n vertices, and then use induction. For the purposes of this theorem, let's define the maximum real root of the empty graph's clique polynomial, which is just a constant 1, to be negative infinity. By doing so, we see that our base case, n equals 1, satisfies the theorem, as there is a single root to the clique polynomial 1 plus x, and that is negative 1, which is obviously greater than the maximum root of the clique polynomial of the only subgraph, the empty graph, at negative infinity. For our second case, n equals 2, there is clearly a solution to the clique polynomial of the only two possible graphs on two vertices. Also, for both graphs, the maximum real roots of their clique polynomials are greater than or equal to those for their induced subgraphs' clique polynomials. For the inductive step, we'll use the first expression we covered in my previous video. Assume the statement we're trying to prove, in red, is true for graphs with n vertices. Then, suppose that we have a graph G with n plus 1 vertices. The graph G without V is an induced subgraph of G with n vertices. So by our assumption, it must have a real root, and so must have a maximum real root. Call this maximum real root R, and now substitute R for x in our expression at the top. This term becomes 0, as R is a 0 of the clique polynomial of G without V by definition. And this factor must be non-negative. Why? Because if it were negative, that would imply that the maximum 0 of the clique polynomial of the subgraph induced by the neighborhood of V occurs to the right of the maximum 0 for the clique polynomial of G without V. Yet that is a contradiction of our statement, which we assume to be true for graphs with n vertices. The neighborhood-induced subgraph is an induced subgraph of G without V, meaning that, by our assumption for case n, its clique polynomial's maximum real root is less than or equal to R. If it is equal, then when we evaluate it at R, it is 0. And if its maximum real root is less than R, then when we evaluate it at R, it must be positive. So, if this factor must be a non-negative number k, and of course R itself is negative because clique polynomials can only have negative real roots, the left-hand side of the equation must not be positive. That means that the clique polynomial of the graph on n plus 1 vertices, evaluated at the maximum real root R of one of its n vertex induced subgraphs' clique polynomials, is equal to 0 or is negative. And if it is negative there, and positive at x equals 0, then it must have some negative real root. Not only that, but it must have a real root greater than R, which is certainly greater than or equal to R. If it is 0 there, then it has a negative real root at R, which is of course still greater than or equal to R. What this means is that the maximum real root of the clique polynomial of an n plus 1 vertex graph is greater than or equal to that of any of its n vertex induced subgraphs. But any subgraph of the n plus 1 vertex graph is either an n vertex induced subgraph or a subgraph of an n vertex induced subgraph. That fact, along with our assumption that the max real root of the n vertex induced subgraphs clique polynomials are all greater than or equal to the max real roots of their induced subgraph of any size clique polynomials implies that the max real root of an n+1 vertex graph's clique polynomial is greater than or equal to that of any of its induced subgraphs. This proves our theorem for all non-empty graphs. Why is this theorem powerful? Well, Tehrans theorem for triangle-free graphs basically arises as a special case of this theorem. If you haven't seen it yet, Tehrans theorem for triangle-free graphs says that the maximum number of edges in a triangle-free graph on V vertices is the floor of V squared over 4. Now that we know that all clique polynomials, except for that of the empty graph, have real roots, suppose we have some triangle-free graph. Then its clique polynomial is a quadratic, where E is the number of edges in the graph and V is the number of vertices in the graph. Using the quadratic formula, we can write out the following expression for its solutions. We know that solutions exist, so the discriminant must not be negative. Squaring both sides, that means that V squared is greater than or equal to 4E, or E is less than or equal to V squared over 4, giving us the same upper bound for the number of edges in a triangle-free graph as Tehrans theorem. Moving on, let's look at the second and final theorem we're going to cover in this video, relating the maximum real roots of the clique polynomial of a graph to those of the clique polynomial of its spanning subgraphs. Remember that a spanning subgraph is one that contains all the vertices of the original graph, but only a subset of its edges. The theorem is this. Let G be any undirected simple graph, and let R be the maximum real root of G's clique polynomial. Now let H be any spanning subgraph of G, and W be the maximum real root of H's clique polynomial. Then W is greater than or equal to R. In other words, the max real root of H's clique polynomial is greater than or equal to that of G's clique polynomial. Let's see an example. Say we have a graph like this. What is its clique polynomial? This is its clique polynomial. What is the maximum real root of this polynomial? Negative 0.5. Now, let's take a spanning subgraph. What is its clique polynomial? Here it is. And note that the max real root is indeed greater than that of the entire graph's clique polynomial. Let's prove the theorem shown at the top of the screen now. From the theorem we proved earlier, we know that G's clique polynomial has at least one real root and that it is negative. We also know that the max real root of any graph's clique polynomial is greater than or equal to the max real root of any of its induced subgraphs' clique polynomials. We also know that this expression is true from my previous video. Now let R be the maximum real root of a graph G's clique polynomial. Then substitute R for x in our expression. The left-hand side is 0, as R was defined to be a 0 of G's clique polynomial. This factor here must be non-negative because it is the clique polynomial of an induced subgraph of G, meaning that it experienced its max real root at some point less than R or at R by our earlier theorem. That means that it will be greater than or equal to 0 for any value of x greater than or equal to R. Also, R squared is always positive, so that means this entire term is greater than or equal to 0. Subtracting it from both sides, we find that the clique polynomial of the spanning subgraph of G with one less edge than G is 0 or negative at the maximum real root R of the clique polynomial of G. That fact, along with the intermediate value theorem and the fact that any clique polynomial evaluated at 0 is 1, implies that the max real root of the spanning subgraph's clique polynomial is greater than or equal to the max real root of the clique polynomial of the original graph. Since this is true for spanning subgraphs missing a single edge, and since we can represent any spanning subgraph of G by successive applications of removing a single edge, this proves that the max real root of the Clique polynomial of any spanning subgraph is greater than or equal to that of the original graph's Clique polynomial. Why is this theorem important? Well, for one, it lets us create a test for Hamiltonian cycles in graphs just by using the Clique polynomial of the graph. Hamiltonian cycles can be thought of as spanning subgraphs with as many edges as there are vertices in the original graph. For example, a Hamiltonian cycle in a 6-vertex graph is a spanning subgraph with 6 edges. Generalizing, a Hamiltonian cycle in a V-vertex graph is a spanning subgraph with V edges. This means that its Clique polynomial is 1 plus Vx squared. The max real root of this Clique polynomial is this, by the quadratic formula. -1 plus the square root of 1 minus 4 over v all over 2. So, if the max real root of the Clique polynomial of the original graph is greater than that number, we would have a contradiction with the theorem we just proved, that the max real root of a spanning subgraph's Clique polynomial is greater than or equal to that of the original graph's Clique polynomial. That means that if a graph contains a Hamiltonian cycle, its Clique polynomial's max real root must be less than or equal to this number, where v is the number of vertices in the graph. That's it for this video. In my future videos, we'll take a look at the conormal product of graphs. I've posted the paper where I found these Clique polynomial theorems in the description if you're interested in digging into Clique polynomials yourself. Thanks for watching. Please subscribe, like, share, and comment if you liked the video. Have a great day.